SwayamPrabha. Digital India. Educated India.
सहनावतु सहनौ भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, this will be the second lecture on our series on mechanical measurements. We would like to just recapitulate some of the things we did in the first lecture. It was mostly introductory in nature. It introduced the topics which are going to be covered in module 1, and then we started off with a description of the reasons why one wants to do measurements. It was followed by the basic idea of measurements, and also it described what to expect in a measurement. Usually the measurements are accompanied by some errors. We identified two types of errors, the systematic as well as the random, and the systematic errors give rise to what is called bias, and the random errors give rise to random fluctuations, and they are statistical in nature. So, the whole idea was to look at these two different types of errors and see what we can do, how we can analyze the data, taking into account that there may be bias and also random errors. The bias can be eliminated or reduced by suitable manipulations. However, the random errors are going to be present, whatever may be the care we have taken in making the measurements, and we require to look at these random errors by what is called a statistical analysis. So, what we are going to do in the present lecture is to continue that topic, and we are going to look at the errors, their distribution, how to analyze them statistically, and also how to characterize these, and also how to obtain the best possible measurement from a given set of data. We will describe this in more detail as we go along. I will also take one or two examples to highlight what we are doing. So, to just spell out, we are going to look at the error distributions with some typical example, and I will also follow it with a general example, and then I will get into the statistical analysis of measurement errors. So, we are going to ask ourselves the question like, what is the best estimate for a measured quantity, and you may now notice that I am using a term estimate. So, this particular term is going to be used very often. We never say that we have a correct or the right value for the measured quantity. We always call it an estimate, because the measurement gives only an estimate for the measured value, measured quantity. So, the idea is to find out what is the best estimate from the measurements we have performed. It may or may not be exactly equal to what is expected or what is the true value of the measured quantity. And then if we are able to eliminate or reduce the bias which may be there in the measured values by a suitable method, then we will be able to estimate the errors in the measured quantity. These errors are due to the random fluctuations, and therefore, the estimate and the estimation of the errors accompanying the measurement are what we are going to look at, and we will follow it with a typical example which will be highlighting whatever we will have discussed by then. So, we will take a look at a typical example. This example is an actual data which has been taken from a reference, and what we have done in this particular example is to take a look at the comparison between the temperature and the output in millivolts from a standard reference thermometer, which is shown by the black curve or black line here, and we have compared it with the data obtained from an individual thermocouple, which is an instrument which is used for measuring temperature, and the black dots here are the actual data that has been collected or gathered. And you notice that in the along the x axis we have the temperature, which is varying all the way from about room temperature here about 25 or 30 degrees, and it is going all the way up to 500 degrees, and we have collected data by changing the temperature to which the thermometer has been exposed systematically from a value of around the room temperature here to the maximum about 500 degrees at the other extreme. As you can see here, the outcome of the experiment is shown in the form of a plot, and there are three things on the plot. One, the black line, which is the output from a standard reference which has been used as a comparison. There are black dots which are actually the data points obtained by taking the readings from the individual thermocouple which has been used in this particular experiment. I have also shown a dashed line which is supposed to represent the general trend of the data shown by the dots. So, we have three things here: the black line representing the reference, which is assumed to represent in some sense the truth. We have secondly the dots, which represent the actual data gathered by the individual from the individual experiment, and then we have the dashed line, which is supposed to represent the trend of the data, the general variation of the data. What we notice from this figure is that there is a systematic difference between the black line and the dashed line. So, between the black line and the dashed line is supposed to represent the general trend of the data, and of course, we will come later to the question of how to get this trend and what is the method we are going to use. This will be discussed later on, but right now let us assume that we have somehow got a trend, and then there is a systematic difference between the black line and the dashed line. This is the bias, and of course, in this particular example the bias is a function of temperature. At 300, for example, the bias is this much, and at 400 degrees if you go here, we will see that the bias has already changed, and if you go to 500, further there is a change in the bias. Therefore, bias is in general can be a function of the variable on the x axis, which usually is going to be the one which we are going to control. The output, on the other hand, which is shown on the y axis, is the one which we are going to measure by keeping the control variable at a constant value as shown in the x axis. You will notice another thing, that the black dots are not lying on the trend line at all. So, the black dots are distributed around the trend line and possibly more or less evenly distributed on the two sides of the trend line. That means that the difference between the black dots and the value represented by the dashed line can be either positive or negative, can sometimes be small, sometimes it can be large, as you can see here. So, the error between the trend line and the black dots is what I call as the error, and this error is due to random fluctuations. Just to explain it a little further, suppose I were to do the experiment at, let us say, at 300 degrees, and if I repeat the experiment again and again, this black dot is only one such value which I have got. I will get a set of values at this particular value of 300, which will vary. It will not give the same value as shown by this black dot. It will keep on fluctuating, keep on varying. Each experiment you repeat, you will get some variation, and that is one kind of variation. The second kind of variation is when you change the temperature. At each temperature you get a fluctuation. So, these two fluctuations, if you assume that they are going to be related to each other, that means that they are going to come out, they are basically due to the same randomness in the experimental experiment which we are carrying out, the two are going to have roughly the same statistics. This is going to play a very important role when we discuss more fully the way we are going to construct the trend line in this particular case. So, this is basically what you are going to expect from any measurement, and in this case I have taken a specific measurement of comparison between a thermocouple which is used to measure the temperature and a standard reference which is also used to measure the same temperature. The assumption being that at any instant of time the standard reference as well as the individual thermocouple are exposed to the same temperature on the outside. So, now with this background, let us look at the next slide which indicates a general example. So, the next example, which is a general one, is slightly different in the sense that the relationship is not any close to a linear type of relationship which we saw in the case of the temperature measurement. In this case, the trend could be a curve instead of being more or less a straight line as in the previous case, and therefore, it is a more general case. I have identified the measured data by the blue circles or blue dots. The blue line is the trend line as we did in the last slide, and then we have the green line which is supposed to represent the truth or the expected the correct value we should have got if the measurement had been done properly without any bias. So, if the bias were not there, what would have happened is that the blue dots would have been distributed around the true value. That means that this green curve here, the blue dots would have been distributed around that. Instead of that, what we see is that the blue dots are distributed not on the green curve, but on the blue curve. Of course, the blue curve, how to obtain it will of course be looked into later on. And in fact, I have fitted data with some polynomial which will of course be taken care of a little later. We will come back to that when we are ready to do that. Now, this same figure can be plotted in 2 or 3 different ways to highlight what we are talking about. The next one shows the difference. So, what we have on the y axis, I have only plotted the error. That means that the difference between, if you go back to the previous one, there is a difference between the blue curve and the green curve. There is a difference between the blue points and the green curve, and I am just highlighting this. I am just trying to plot the difference rather than the value itself. So, the advantage of that is that it magnifies usually the differences, and you can clearly see what is happening. The bias now comes out as this curve, the trend line which we had the blue line there. Blue line and the green line, the difference or the distance between the two is of course varying with respect to x, and it comes out as a curve like this, and the bias is clearly seen here. And you also see that the blue dots are distributed around the bias in a systematic fashion like that, in some kind of a random fashion, but the difference here is smaller, here is bigger, and so on. The bias seems to be, the difference seems to be a little larger here. Of course, it should be due to only accidental reason. So, let us look at another way of making a plot. The another way of making a plot is just to isolate the random error. That means they take the fluctuation. In the previous case, we took the difference between the points and the green curve. If you remember, the green curve was the truth. We took the difference between these two or these two. In the next case, I have taken the difference between the green and the blue curve. In the next one, I am going to take the difference between the blue dots and the blue curve. So, you see that the random fluctuations are distributed in a certain fashion. Of course, this is quite accidental that these values are obtained. If you were to repeat the experiment, these dots will not be in the same places. Some of them may change. For example, this may come down, this may go up, and so on and so forth. So, every time you repeat the experiment, you will get a different set of such blue dots. That means the key to this whole analysis is to repeat the measurement again and again, and each time you repeat the measurement, you are going to get these blue dots distributed not the same way, they are going to keep on changing. But this blue dots will have some statistical property, which is what we would like to look at. For example, if you go back to the slide, you see that if I were to project all these blue dots onto the y axis, if I were to project these like this, I take a straight line here, put it here, another here and so on, you will see that the dots will be distributed along this line in a certain fashion. So, we would like to know what is the distribution of these blue dots on the y axis. Can we characterize this distribution mathematically, and if so, what are the characteristics of that particular curve? These are going to be important if you want to understand the errors and their behavior and their characteristic. So, with this in view, let us see what one may expect. It is not that every time we are going to expect this, but if we were to do the experiment again and again, and if the method of measurement is not different each time, if we are going to have a uniformly careful experiment made, every time we repeat the experiment, we do it with the equal care, then we can expect, as you saw here in the previous graph, these dots are going to be distributed in some random fashion, they will form a certain distribution. What is the characteristic of this distribution? The positive errors, the random errors we are talking about, the positive values and negative values are equally likely. Positive large values, negative large values are equally likely. Okay? That means the distribution must show some kind of a symmetry with respect to the 0 line here. So, the random error shows some kind of a symmetry with respect to the x axis or the 0 error axis, and these are going to have a distribution is symmetrical, and the one symmetrical distribution we are very familiar with is called the normal distribution, and I have given the expression for the normal distribution in this slide. So, random errors may be distributed as a normal distribution. If I indicate the mean of the values as mu, so if I go back to the previous slide, the mean is 0 in this case. Of course, mean could be some value. I can subtract it out and make it equal to 0 just for convenience. Okay? And if sigma is the standard deviation with respect to the mean, we will define more fully sigma, and we will find out how to determine sigma from measured values and so on. So, the mean and the standard deviation represented by mu and sigma, the probability density, that is the probability of finding the value of the error given by x is the x minus mu is the error, because mu is in the previous case mu was 0, but x minus mu is the error. The magnitude of the error is x minus mu. The probability with which we can find we can expect to have the error x minus mu is given by this simple function f of x equal to 1 over sigma square root of 2 pi e to the power of minus half into x minus mu by sigma whole square. This we call as the standard or the normal distribution. So, what is the property of this distribution? Immediately you will see that the values here are all positive, x minus mu by sigma whole square is positive. Therefore, whether x minus mu is positive or negative, the value is the same. Therefore, it is satisfying the requirement that the positive errors and negative errors occur with equal probability. A particular value of the positive error and a particular value of negative error will occur with the same probability. Okay? Actually, the probability is given by the area under the curve, as we will see later on, but here this is the probability density function. So, density multiplied by dx will give the probability that the error occurs within that element dx. So, let us look at the properties of this. One other property which you are going to be very keenly looking at would be the total or the cumulative probability of the error. So, if I consider the band from minus x to plus x, so if I go back to the slide which showed the random error distribution, suppose I want to know what is the likelihood that the error is between 0.1 and minus 0.1. So, I want to find out the error, the probability of the error falling within these two values. That can be obtained as an integral as shown here. So, f of x, where x is plus or minus this x value, the integration is from minus x to plus x, f of x equal to 1 over sigma root 2 pi, this is just a normalizing factor, e to the power of minus half v minus mu by sigma whole square dv, v is used as a dummy variable. So, let me just again go through this. This value of f of x, which is the integral between minus x and plus x, gives me the likelihood or the chance that the value of the error is going to lie between a value of plus x and minus x. If you remember what we said earlier, this is a symmetric value, that is, if v minus u is positive or negative, it does not matter, this is the same value. Actually, you can write it as f of x equal to 2 times integral 0 to x if you want. Okay. So, let us look at the next slide, which gives you the graphical representation of the same thing. And what I have done is I have shown both the probability density curve and the probability cumulative probability on the same graph. The green curve here shows the probability density, which is a function which is looks like a bell shaped curve. It is a very important curve which we find in all mathematical, all statistical analysis, and this is called the Gaussian distribution. It is a Gaussian or the normal distribution, is also referred to as a Gaussian distribution because of the person who first proposed this particular distribution, Gauss. The integral is, here I have what I have done is I have taken the integral from minus infinity to a given value of x. So, if you go to the minus infinity on this side, the value will become 0, and if you go to plus infinity, if you go on the other side, it will go to a value equal to 1. That means that the value of the cumulative probability of the value lying in between any value between minus infinity and plus infinity is equal to 1. So, it is also normalized, that means that the total probability is 1, and therefore, the probability which we calculate, for example, when I said between minus 1 and plus 1 or minus 2 and plus 2, these are going to give you the probability of the error lying between. In this case, if you look at the x axis, I have taken x minus mu divided by sigma. I am using sigma as the unit. Therefore, if minus 1 to plus 1 here means the error being within plus minus sigma. If I take minus 2 here and plus 2 here, it is the error between plus 2 sigma and minus 2 sigma. Therefore, and in fact, I have shown this as a separate curve. The next slide also gives me that information. So, this is a different way of putting it. Suppose I want to find out what is the cumulative probability which is on the y axis for deviation in terms of plus or minus sigma. If I am interested in finding out the probability that the deviation is within plus or minus in terms of plus or minus sigma, the curve gives you this one, which goes from of course 0 to 1. If you see here, in fact, in the next slide I have shown some typical values which we call as confidence intervals. Let us go back and let us see what this confidence interval is. The cumulative probability tells me in a large number of measurement, if I were to repeat the measurement again and again, and I were to look at the statistical properties of the error distributed around the mean or the error distributed around the most the best estimate for the value, then the error distribution will follow this cumulative probability curve. And again here I have taken with respect to plus or minus sigma. For example, plus or minus 1 sigma, you see that this is about 64%. So, 64% of the time, or 63, between 63 and 64% of the time, the value of the deviation will be within plus or minus 1. That means I can predict with 64% confidence, with 64% roughly confidence, that the value will not exceed plus or minus sigma. Similarly, if I take 95% confidence, I can say that about 1.9 or so. Plus or minus 2 sigma, you can say that more or less 95% of the errors will be within those two limits, and that is expressed in the form of the confidence intervals given in this particular table. So, the cumulative probability, if the error is 0, do we expect 0 error? No, never, because the error cannot be 0, and therefore, you expect the interval for confidence interval for 0 error is exactly 0. That means that hardly any time, even once, you may not get the value of error equal to 0. That means you are not going to get the best value. Any number of times you make the measurement, you never are going to get the best value. Suppose I want to find out whether 95% of the time what I am going to get, about 1.96 sigma. That means plus or minus 1.96 sigma. This is the confidence interval. 95% of the time I can be sure that the error will be within the plus or minus 1.96 sigma. So, if I take 99% confidence interval, plus or minus 2.58 and so on, about 0.999, 99.9% plus or minus 3.29 sigma. Therefore, in general, we can make the following statement, that if we are going to make the measurement again and again, and each time we look at the statistics of the errors, and we calculate the number of values which are going to be within 99% of the spread in terms of 99% probability, it will be within 3.3 sigma. Therefore, in no experiment will you get, or very unlikely that you will get a value much larger than 3 sigma. Okay? That is one statement which you can make. We can also make the other statement is which is that no time we are going to get a value exactly equal to the best value or the accepted value or the true value. Therefore, these are all some general trends or general features of the distribution, and now let us look at how to use this information to analyze the experimental data. So, it should be clear now by now that the only way we can understand the nature of the errors is to repeat the experiment any number of times, whatever the number of times it is possible. If it is very expensive, of course, the experiment may be done only once or twice, and therefore, we are limited by the amount of time and effort we can spend. But in some simple experiments, you can do it any number of times within reasonable limits, and therefore, that can be done. At least notionally, we can assume that any experiment is possible to repeat it any number of times, so that the nature of the errors can be obtained by looking at the sample of data. We call it a sample because we can repeat the experiment and get another sample, another set of data, and so on and so forth. So, this is called sampling, and unfortunately, we do not have too much time to go into the details of statistical analysis to a depth which is desired maybe in a higher level, but here we will just look at some of the things we can achieve by not doing a very study in great depth. We will try to find out what is required for us by looking at simple things. So, we will assume that a certain quantity x is measured repeatedly, and what I have from these measurements is a set of values x I. I stands for the experiment number, the time I equal to 1 to n. That means, first time I did the experiment, I got a value x I, second time I got x 2, the third time I got x 3, and so on up to n number of times, then x n. Therefore, I have, by repeating the data, we get what is called replicate data or repeated data for I equal to 1 to n. What we will notice once we get a data like this is, because of random errors, these are all going to be different. Of course, many of them may be close to each other, and if we round off, for example, some of them may be actually they look like they are alike, but if you use a sufficient number of number of digits on the decimal point and so on, you can actually see the differences. Of course, in any experiment we may use a certain number of decimal point to represent the number, and therefore, within that there may be some which may appear to be the same, but in general these are all different values. These are different values of the same measured quantity obtained by repeating the experiment again and again, assuming that the repetition is possible, not very expensive. So, the question we are going to ask is, how do we find the best estimate for the true value of x? Why am I using the term estimate? Because I am not going to get the true value. I am very clear about it. All I can do is to estimate a value which may be expected to be close to the true value. Whatever may be the true value, we do not know. So, we are happy if we can get an estimate which is the closest to the true value, and I may or may not be able to know how close it is. It depends on the particular experiment and so on. So, let us look at the principle involved behind this particular estimation, and that requires a little bit of understanding of the nature of the errors. We have already said that the errors are distributed in a normal fashion, and therefore, if I go back to the experiment which was given in an earlier slide, of course, here I have varied the x, it does not matter. If you were to just take the values and project it onto the y axis, I said earlier that we are going to get a certain density of these points are going to lie on this, and if you divide this 0 to 0.15, for example, if I divide into 3 ranges, let us say 0 to 0.05, 0.05 to 0.1 and 0.1 to 0.15. Similarly, on the negative side also I can do the same thing. So, 2 points are lying in this particular range 0 to 0.05. One point is lying between 0.05 and 0.1, and 2 of them are lying between 0.1 and 0.15. Of course, if I were to repeat the experiment, these values may be different. Okay. So, what I am going to look at now, I am going to ask myself the question, why is it that I got these two values between 0.00 and 0.05? I got these values because it was a probable outcome of the experiment. The experiment was such that these values had to occur, and if it were to occur, if these errors were to occur according to the normal distribution, then what I can do is I can use the normal distribution which is shown here, and what I have done is I have written it in a slightly different form here. So, the value of x equal to x1 occurred with a probability equal to 1 over sigma root 2 pi e to the power of minus xb minus x1 whole squared by 2 sigma squared. Notice that I do not know xb, I do not know sigma. I am just assuming that the values were distributed according to normal distribution with a given sigma, with a mean value or the best value xb. Both of these are not known at the moment. So, what I am saying is that the probability that the value laid was x1 was obtained is given by this factor multiplied by sigma root 2 pi. The value x2 occurred by a probability given by this factor multiplied by another sigma root 2 pi. Because I am having n such data point 1 to n, I will have sigma root 2 pi to the power of n as the denominator, because each one is going to correspondingly contribute sigma times root 2 pi. In the numerator, I am going to have a corresponding exponential factor e to the power of minus xb minus xn whole squared by 2 sigma squared e to the power of minus xb minus x2 whole squared by 2 sigma squared and so on, multiplied by dx1 dx2 etc. These are the width of the interval I am going to use in that. If you remember, I said 0 to 0.05, 0.05 to 0.1 and so on. These dx are arbitrarily chosen to, for our convenience we can choose arbitrarily. Therefore, dx1 dx2 etc. dxn are all quite arbitrary. I can choose a small value here, a large value here and so on, depending on the distribution. Now, what I want to do is to find out, in the particular experiment I got the values x1, x2, xn. Why did I get these values? I got the values because this was the most probable. That means that probability of getting that outcome, which is a set of measured values x1, x2 up to xn, this was obtained only because it was highly probable. If it were not highly probable, how would I get those values? I should not get. Therefore, I am going to make the hypothesis that this cumulative probability must be a maximum, because I was able to get this outcome of the experiment as the values of x1 to xn given by the data which I have collected. So, this is the basis for our analysis of the statistical nature of the data. Therefore, there are two quantities xb and sigma, both of which are not known at the moment. So, I am going to make the assumption that if I were to maximize this, and you can see here that this can be written in a more succinct fashion, 1 over sigma root 2 pi to the power of n, exponential of this is like adding x to the power of e to the power of this plus this plus this. So, I am showing it as e to the power of minus sigma 1 to n xb minus xi whole square divided by 2 sigma squared multiplied by the product of the intervals. And because these are arbitrary, the cumulative probability will be maximum only if this factor is maximized. This factor 1 over sigma root 2 pi to the power of n e to the power of minus sigma 1 to n xb minus xi whole square divided by 2 sigma squared is going to be maximum. I am going to give two types of arguments here. I am going to first look at the maximization of this term by mathematically performing the required derivative, taking the derivative and setting it to 0. Then I will also give a physical explanation of why we do that. So, that will be explained in on the board. I am going to use the board for that. So, let me use the board and show how we are going to do this little bit of mathematics. If you go back to the slide, you will notice that we have two factors, the exponential factor multiplied by 1 over square root of sigma root 2 pi to the power of n, and exponential minus sigma equal to 1 to n, the sum of the squares divided by 2 sigma squared, dx1 dx2 etc. for the product on the other side. We need to look only at the first part. dx1 dx2 dx etc. dxn is not going to concern us. So, let us write down the cumulative probability as being proportional to, it depends on two parameters, the value xb and sigma, and this is given by, this is only one factor I am going to write, this will be 1 over sigma to the power of n square root of 2 pi to the power of n exponential of minus sigma I equal to 1 to n xb minus xi whole squared divided by 2 sigma squared. So, we have to maximize this. What are the two things we have to choose? We have to choose by choosing by the right choice of xb and sigma. So, I am trying to find out what is the best value xb for the variable or for the quantity I have measured, and the sigma which best represents the distribution of the errors. Okay. So, I will require dou p by dou xb equal to 0. This will become, this does not contain any xb, therefore, it will remain as such. So, it is not going to be playing a role as far as this particular is concerned. E to the power of something will give the same quantity. So, I will not write it fully, I will just write like this, whatever is inside multiplied by, I am going to take the derivative of this term by term with respect to xb, because the derivative is only with respect to xb. So, that will give you sigma I equal to 1 to n, this minus sign I can write it outside here, 2 multiplied by xb minus xi. So, each term is going to give me 2 into xb minus xi, sigma I equal to n to n, this must be equal to 0, or you can see that sigma I equal to 1 to n xb is equal to sigma I equal to 1 to n xi, because this portion cannot go to 0, only this can go to 0, and what I have done is I have to write this here. So, sigma I equal to 1 to n x b, x b is the same value, I equal to 1 it is x b, I equal to 2 it is x b, therefore, this can be written as n times x b, or I can say that x b, the best estimate for the measured quantity is equal to sigma I equal to 1 to n x I divided by n, which is nothing but the mean or the x bar, which is the mean. Therefore, we have shown by using the maximization of the cumulative probability that the best value which you can consider the estimate or the best estimate from the set of replicate data is given by the mean, which is nothing but sigma I equal to 1 to n x I divided by n. Let us look now at the evaluation of sigma. We have only done part of the way. We have looked at the best value. Now, what is this sigma? Sigma should represent the best estimate for the error. So, I am going to now look at how to obtain that. That can be done by simply taking the derivative with respect to sigma into x b and then writing the expression, and we will do that in the next page. So, for this we have to do is to take sigma. There are two factors. The first factor also contains sigma, therefore, that will also contribute to the expression. This will be 1 over sigma to the power of n plus 1 with a negative sign, of course, square root of 2 pi to the power of n. If you want, you can leave out this, because it is going to come in each term and it is not going to contribute. This will be multiplied by exponential of the term which is already there. Now, the next term is going to contribute, because x b minus x I whole square divided by 2 sigma squared, that sigma is also going to take part in the differentiation. So, the next term will be, there will be 2 minuses which will come and make it a plus, and therefore, it is going to give you the following. Sigma x b minus x I whole squared I equal to 1 to n sigma squared. Let me just write it properly. It is 2 sigma squared there, that will give you sigma cube. Then there is 1 sigma to the power of n outside. So, this will become n plus 3, and this must be multiplied by exponential whatever term we had, and of course, 1 over square root of 2 pi to the power of n. This must be equal to 0. So, this exponential factor as well as this 1 over 2 pi factor is going to be common, and that is not 0. Therefore, this term and leaving out this term must be added to get 0, and therefore, if you do that, this n plus 1, n plus 3, it will give you sigma squared. Sigma squared is equal to, you will get the value I equal to 1 to n x b minus x I whole squared divided by n. That means, or you can also find out the standard deviation as the plus or minus square root of this quantity. This is nothing but the variance, which is always a positive quantity. The standard deviation can be plus or minus, because the error could be either in the negative direction or the positive direction. We have already seen that, and we have also seen that the negative and positive errors must have similar probabilities. And what we have found is a very interesting and important relationship. This x b is already determined in the previous slide we showed. X b is nothing but x mean. So, I can replace it by the mean value. So, what this is indicating is that the variance sigma squared is this value and the standard deviation is this. In fact, you can see that this is the least value for the variance or the least value for the standard deviation. So, we will make a note here that this is the least possible value. Why is it the least possible value? Because the variance with respect to the mean is the smallest you can think of. Okay? Therefore, it is the least value. So, with this background, let us go back to the slide show, which was indicating the cumulative probability. This is where we took off and we went to the board to make a few calculations. And let us look at the next slide, which gives you what is called the least square principle. So, what we did by digressing and looking at the optimum or the best possible situation by finding out the values of x b and sigma, the best estimate for the measured quantity and the best estimate for the variance or the standard deviation. It was done by taking the derivative of the cumulative probability with respect to x b and sigma and then finding out what are the best estimates for the two quantities. And if you remember what I said just before we took off from there, I said that the variance is the least when you calculate the variance with respect to the mean. That means, the least square principle or the least square principle means that the variance with respect to the mean or variance which you calculate from the set of data you have got must be the smallest you can think of. How do I do that? Let us look at the next slide, which gives me another alternate way of looking at it. So, the alternate way of looking at it is to say the following. Suppose I have been doing the experiment very carefully. I have taken care to choose the proper instruments and so on. I have made sure that everything is properly arranged. No disturbances are allowed to interfere in our measurements. Then what should I expect? I should expect like the sharpshooter. Remember the last class I talked about the target practice. You had 3 people there. One who was good at target practice, target shooting. The second fellow was like any of us, he did not have any skill whatsoever. A third fellow who had skills, but not properly honed. So, in the case of the fellow with the best skills, you could see that all the values were coming within the bullseye. So, if I am a careful experimenter, I should expect that I must have a small variance. The precision must be large or it should be very highly precise. So, what I am saying here is it is reasonable to assume that the best value must be such that the measurements are as precise as they can be. That means that I want my measurements to be very precise. I do not want it to be termed as imprecise. So, I am expecting it because I have done the experiment very carefully. Therefore, the least square principle, there are 2 ways of looking at it. One is from the distribution of the errors, looking at the normal distribution and its properties, then looking for the largest cumulative probability, or I can say that I want to have the best precision possible because I have done the experiments very carefully. So, thus we minimize the variance with respect to the best estimate x b of x. So, this is another way of looking at the same thing, which is somewhat physical the other one was more mathematical, which came from the principle of maximizing the probability. So, if I minimize the variance, I am not dividing it by n, it does not matter, and also this lower case n sometimes uppercase n. So, they are one and the same. If there is a uppercase or lower case, do not be worried about that. I am going to look at this what is called the sum of squares of the error. So, S is equal to sigma equal to n x b minus x I whole squared. I want to minimize this by choosing the proper value of the x b, and that is what I have indicated by a very simple process, and it is seen that dou s by dou x b equal to 2 sigma equal to n x b minus x I into 1 equal to 0, which gives you x b equal to the mean value. So, we get back the value, the best value for the estimate for the value is nothing but the mean of the individual measurements. So, this is an alternate way of getting it. We will round off the discussion of this particular in this lecture by giving a simple example. I have taken the example of measuring resistance of a certain resistor. So, what I am doing is I am taking the same resistor, I am not taking different resistors. I am taking the same resistor, I am making the measurement of the error, the resistance of the resistor. Actually, I am repeating the experiment. Okay. You can also take resistors from the same lot, same value, and do that. That is a different one. We are not talking about that. That has something to do with quality control. Here we are talking about the measurement process. So, in this example, you see that the experiments are repeated 9 times, 1 to 9. The values of the resistance in kilo ohms was determined again and again. I had 1.22, 1.23, 1.26, again 1.21, 1.22 was repeated thrice, then I got 1.24 and 1.19. So, we can see that there the smallest value I got was 1.19 in one of the experiments, and the biggest value was 1.26. So, the range of the values is the minimum and the maximum are 1.19 and 1.26. Now, the question is what is the best estimate and what is the error with 95% confidence. So, the best estimate is of course given by the mean, which is calculated by as shown here. So, R bar is the mean of the value, is 1.22 into 4, there are 4 values, 1.23 occurred once, 1.26 occurred once, 1.24, 1.21, 1.19 divided by 9, that gives you a value of 1.223. I am going to deliberately round it up to 1.22 because I cannot expect a better value than the second decimal place accuracy. Okay. So, with that assumption, we will say that 1.22 kilo ohm is the best we can estimate, best estimate we can get from this set of measurement. It is also known from our earlier discussion that the standard error sigma or the standard deviation of the error sigma is given by the variance being the least when you take Ri minus R bar whole squared 1 over 9 sigma 1 to 9, that gives you this value 3.33 in 10 to the power of minus 4, and the value of sigma is 3.333 in 10 to the power of minus 4 square root, it gives you 0.0183. I am going to deliberately round it off to 0.02 kilo ohms. Therefore, I can say that with 95% confidence, the best value I can think of for the resistance is the value which I obtained in the previous slide, 1.22 kilo ohms plus or minus 1.96 sigma, which is 1.96 into 0.0183, which I am going to round it out to 0.04 because it is 0.036. I am going to round it out to 0.04. So, I can say that the value of the resistance, the best estimate is 1.22 kilo ohm, and the error I can expect is about 0.04 kilo ohm. So, 4 units in the second decimal place. I think we will stop here in this particular lecture, and in the next lecture we are going to look at an important aspect, that is the propagation of errors, and once we have looked at this idea about propagation of errors, we will look at the regression analysis, which forms a very important part of presentation of data. Thank you.